My dear students, I welcome you again to the second lecture on high voltage direct current transmission systems, HVDC systems. In our last lecture, we have discussed various advantages of HVDC systems over AC power transmission at high voltages. We have also discussed some of the drawbacks of HVDC systems, practical applications of HVDC systems, and finally the economic aspects, the economic factors. Now let us today discuss various types of HVDC systems. We classify HVDC systems like this. Types of HVDC systems or HVDC links. Any HVDC system is also called an HVDC link. Broadly, there are three types of HVDC links or HVDC systems. They are classified as like this: monopolar link, second type is bipolar link, and the third type is homopolar link. Homopolar link. These are three types of HVDC systems or three types of HVDC links: monopolar link, bipolar link, and homopolar link. Let us discuss them one by one, and finally we will decide which link is most popular and most widely used. We will start with monopolar HVDC link, or what we call as monopolar link. This is what we discuss first. Monopolar HVDC link, or simply we call it monopolar link. Mono means one, so it's quite obvious that a monopolar link means an HVDC transmission system which comprises of only one conductor. And in this case, in HVDC terminology, the conductor is also called pole. So there is a single conductor or single pole, and ground is used as a return path. So schematically, it looks like this. This is the schematic diagram of an HVDC monopolar link. This it has two converters. One converter is here and another converter is on the other side, on the other end. And both the converters are supplied from AC system. There's a three-phase AC system on this side and three-phase AC system on this side. This line or conductor or pole may be hundreds of kilometers as far as its length is concerned. Now this converter may operate as a rectifier and this converter may operate as an inverter. So therefore this forms our rectifier station and this forms our inverter station. What happens? The three-phase AC is converted into DC, and then this DC power is transmitted over long power transmission line or pole, and then this DC is again converted back into AC with the help of this line commutated inverter, and then it goes to various substations where from power distribution takes place. Now it's monopolar link because it comprises of only one conductor or one pole, and this pole is usually of negative polarity, with ground or C used as the return path. You can see in this case ground is used as a return path. Only one conductor or one pole is used. Negative polarity results in less corona. Why negative polarity? Why not positive polarity? Because negative polarity results in less corona loss and less radio interference. That is the advantage with negative polarity of the conductor. So this is the simplest type of HVDC link or HVDC system. Only one conductor has to be laid and ground or C used as a return path. But the problem with this type of HVDC link is that in the event of fault on this pole, suppose this pole develops some fault, or one of the two converters develops some fault, in that case the power cannot be transmitted over the pole, because if there is a fault on the pole, it's not available for the transmission of power. So therefore complete blackout or complete shutdown occurs. So therefore monopolar link is very less reliable as far as reliability is concerned. A fault on the pole will result in complete shutdown. No power transmission will take place unless the fault is rectified or cleared. So therefore it is highly unreliable and it is not very popularly used. Okay, so that was the first type of HVDC system, monopolar HVDC link. The second type is bipolar HVDC link or bipolar link. The name itself indicates that bi means two. It comprises of two poles or two conductors. One will be of positive polarity and another will be of negative polarity. So therefore it is a bipolar HVDC link. So its schematic diagram looks like this. You can see this is the schematic diagram of a bipolar HVDC link. You can see there are two poles. One is positive pole plus and another is negative pole minus. Both carry the current, DC link current or DC line or the transmission line current denoted by ID. Now we can see in bipolar link, each terminal, it's a two terminal HVDC network. This is one terminal and this is another terminal. Each terminal comprises of two converters which are connected in series and they share the voltages equally. Similarly, on this side, we can see there are two converters which are connected in series and they share the voltage. They have the equal voltage ratings, right? Now, if power flow is from this end to this end, that is this converting station to this converting station, in that case, these converters will act as rectifiers. And therefore, the converters on the other side, they have to convert DC power back into the AC power. So they will act as inverters. I stands for inverter. However, if the direction of power flow reverses, power flow can interchange. It can change its direction. Sometimes it can flow from this end to this end, and sometimes you may make power to flow from this end to this end, depending upon the requirement of the power. If the direction of power flow reverses, it flows from this end to this end, in that case, this will act as rectifier. R stands for rectifier, and in that case, this or these converters will act as, they will work as inverters. So that means whether the converters at a particular converting station will act as rectifiers or inverters depends upon the direction of power flow. If power flow is from this end to this end, these converters act as rectifiers and these converters act as inverters. If the direction of power flow is from this station to this station, in that case, these converters will act as inverters and these converters will act as rectifiers. Now the middle points or the junction points between the two converters at each terminal. These are the junction points. They are generally grounded on both the sides. So you can see this with the help of grounding rods, the junction point of these two converters, it's grounded. Similarly, the junction point or the neutral point on this side is also grounded. So that makes these poles independent poles. This pole along with the ground becomes an independent pole. This pole along with the ground becomes an independent pole. Normally, when there is no fault in the system, an equal magnitude of current will flow in both the poles. That means this plus ID will be exactly equal to minus ID, and in that case, there will be no current flowing through the ground. No ground current will flow. However, in the event of fault on any of the two poles, let's suppose there is a fault on this pole. So this pole is out of service. It has tripped because of the fault. However, you can still make power transmit over the system using ground as the return path. This pole it has not developed any fault. It's a healthy pole, and this pole has developed fault, so it is not operating. So this pole along with ground can be used for transmitting about half of the rated power on the system. So therefore, half of the power can still be transmitted with ground as the return path, and in that case, it works like a monopolar HVDC link. In case of monopolar HVDC link, one very important point I just forgot to tell you, that one of the drawbacks I told you, that in case of monopolar link, if the pole develops some fault, there is no transfer of power. So the entire system shuts down. So it's less reliable system. Another problem is that since ground is used as a return path, the flow of currents through the ground is objectionable, because when the current flows through the ground, there are pipes, cables, and other objects generally buried under the ground. And when this ground current flows through the pipes, it flows through the cable sheets, etc., it causes the corrosion of the pipes, corrosion of the cable sheets, and corrosion of other metallic objects which are buried inside the ground. And it also results in the induced voltages. And in case of broken ground rod, if this ground rod is broken, other problems also occur. That's another drawback with monopolar HVDC link. That is why monopolar HVDC link is generally not used. In case of bipolar HVDC link, under normal circumstances, when there is no fault, although both the sides are grounded, but there is no flow of ground current. No current flows through the ground. Only in case of fault on one of the two poles, ground can be used as return path temporarily till the fault is cleared, so that the system does not shut down. Still half of the power is transmitted over the system. So therefore, this system is highly reliable. Okay, so this is about bipolar HVDC system. And these bipolar systems are generally denoted, their voltages are denoted, say, for example, plus minus 100 kV. Plus minus means this is positive pole, this is negative pole. So 100 kV, both poles are at 100 kV. So that's why we use this plus minus 100 kV. And I have already told you that in India, a very popular HVDC link, which is a bipolar link, is plus minus 500 kV. I'm repeating, it is from Dadri to Rehand. Another recently commissioned bipolar HVDC link is plus minus 800 kV. It is connecting Agra to Northeast. It's a long power transmission line, HVDC link. It's a bipolar link, and voltage rating is plus minus 800 kV. So that's about bipolar HVDC link. The third type of HVDC link I'm going to discuss with you now, that's called homopolar HVDC link. Homopolar link. It's obvious from the name itself. Homo means same. Homopolar means it may have two or more than two conductors or two or more than two poles, each having same polarity. You have seen in bipolar link, there are two poles. One is they are having opposite polarity. One is having positive polarity, another is having negative polarity. But in homopolar link, if there are two poles or more than two poles, they will have different polarity. For example, if there are two poles, they will have same polarity. Generally both are negative. I already told you why negative polarity, because negative polarity of poles results in reduced corona and reduced radio interference. So schematically, a homopolar link looks like this. This is of negative polarity, this is also of negative polarity, this is the direction of current flow, and in this case, this is the direction of, it's like this. This is the direction of current flow. In homopolar link, ground is permanently used. There is always the flow of current through the ground. You can see the current is flowing in this negative link like this. It cannot flow through this converter because this converter has thyristors connected like this. Current always flows from anode to cathode. It cannot flow from cathode to anode. Therefore, this current has to necessarily flow through the ground. Similarly, this current, when it goes here, it cannot flow through this converter. It has to flow through the ground. Therefore, in a homopolar link, we have two poles. In this case, for example, two poles of same polarity, negative polarity usually because of the advantage, and ground is permanently used. There is continuously the flow of current through the ground. Just like in bipolar link, if one of the poles develops the fault, the other pole along with the ground can still be used as a homopolar link, and there will be still flow of power. How much power? 50% of power, rated power. One advantage with homopolar link is that, for example, suppose this pole has developed fault, we have these two converters available with us, we are not utilizing them. There is an arrangement with the help of which these two converters can be reconnected with these two converters parallelly, and if the line has the capacity to carry the power, then more than 50% power, or in some cases rated power with increased line losses, can flow in this monopolar link. The reconnection of converters which are not operating in the event of fault in case of bipolar link is very, very difficult, whereas it's easy in this case. So this offers an advantage of homopolar link to bipolar link. That is, if a particular link or pole develops the fault, the converters belonging to that particular pole can be reconnected with the other pole, and about rated power can still be made to transmit over the remaining pole, right? But the main problem is the flow of current through the ground. Current continuously flows through the ground, which is objectionable because it causes the corrosion of pipes, it causes the corrosion of sheaths of the underground cables, it causes corrosion of other metallic objects, it results in induced voltages, and in the event of broken ground rods or earth rods, other problems. So therefore, homopolar link is not very popular. It's generally not used. So the summary of this is that out of the three types of HVDC links, monopolar link, bipolar link, and homopolar link, bipolar link is very widely used. It's the most popular HVDC link, which is used throughout the world because of the advantages offered by this. Monopolar link is not used because it is not having good reliability. It's very less reliable, and the flow of ground current gives the problem. Homopolar link, same problem, although it is highly reliable, but the ground current has to always flow, which is objectionable, right? So therefore, the most popular HVDC link is bipolar link, and from now onwards, whatever HVDC systems we'll consider, we'll analyze, we'll study, they are exclusively bipolar HVDC systems, bipolar HVDC links. Okay. That was about types of HVDC systems or types of HVDC links. Now let us try to understand various parts, various components, which we call as principal components or parts of an HVDC system. Principal components, or I can write within brackets parts of an HVDC system. To understand what are the various parts, what are the various components of an HVDC system, we have to draw the simple schematic diagram of an HVDC system, and what type of HVDC system I'm going to draw. Obviously bipolar HVDC system or bipolar link, and we will identify various parts, various principal components, and discuss them one by one. So it looks like this. So I will draw three small lines. If 3 means it's a three-phase system. I'm not drawing 3 lines, I'm drawing a single line, and 3 small lines means it's a three-phase system. Actually, there are 3 lines or 3 phases. What are these? These are transformers. So these you can see on this side and on this side, these rings represent transformers. They are called converter transformers. Converter transformers. I will write here converter transformer. These are all converter transformers. What is this? This is harmonic filter. Why do we need it? I will discuss with you. Harmonic filter on both sides. In this station, as well as in this converter station also, we have harmonic filters. What is this? This is called smoothing reactor. Smoothing reactor. What are these? These are grounds or grounding rods, which are buried inside the ground. And these all, this and this, these are converters. So these are various parts or principal components of a bipolar HVDC system, which is very widely used HVDC power transmission system. Various components are harmonic filters, converter transformers, converters themselves, smoothing reactor, grounding rods. These are the main parts. Apart from this, you'll have reactive power systems also there, reactive power compensators, which I have not shown here. Okay, so let's discuss these parts one by one. So the most important part of or heart of the entire system is the converters. So first we will discuss converters. First, converters. You can see we have 2 converters connected in series in this converting station, and we have 2 converters connected in series in other converting station. This converting station may be a rectifier station, and this converting station may be an inverting station or inverter station if power flow is from rectifier station to inverter station, that is from here to here. If power flow is from this station to this station, then in that case these converters will behave as rectifiers and these converters will work as inverters. In that case, this will be your rectifier station and this will be your inverting station. Anyway, whether it's a rectifier station or an inverting station, you will have converters on both the sides, line commutated converters using thyristors, SCRs. Now, converters are the most important part of your HVDC power transmission system. Now, you either use 6 pulse converters or you use 12 pulse converters. I don't know how many of you have studied 12 pulse converters. Definitely in your power electronics course, I'm sure all of you have studied about 3 pulse converters, 3-phase 3 pulse converters, and 3-phase 6 pulse converters, a great converter bridge, which is a 6 pulse converter. But I'm not sure how many of you have studied about 12 pulse converters. Okay, in this course, we will study about 12 pulse converters also. So the most popular converters in HVDC systems are either 6 pulse converters or 12 pulse converters. Actually, you have to make a choice between 6 pulse converters and 12 pulse converters, and how to select, how to make a choice whether to use 6 pulse converter, 3 pulse converter, or 6 pulse converter, or 12 pulse converter. We'll come to that later on. So if you are using a 6 pulse converter, for 6 pulse converter, if your converters on both sides are 6 pulse converters, for 6 pulse converter, you use 3-phase 2-winding transformer on both sides. 3-phase 2-winding transformer. So you use a 3-phase 2-winding transformer, or if you use a bank of single-phase transformers, then you use 3 single-phase 2-winding transformers, 3 transformers. If you have a 3-phase transformer available, use a 3-phase transformer. 3-phase 2-winding transformer, primary winding and secondary winding, all low voltage winding and high voltage winding. But if you have a bank of 3 single-phase transformers, then you can connect them as a 3-phase transformer. So either you use a single 3-phase transformer or 3 single-phase transformers. That's about 6 pulse converter. What about 12 pulse converter? If you have a 12 pulse converter, I will write here for 12 pulse operation. For 12 pulse operation. I hope you know what this pulse number means. 6 pulse means that for one cycle of AC, the output voltage has 6 pulsations in it. 6 pulses in DC output voltage. And in 12 pulse converter, for one cycle of AC, input AC, there are 12 pulsations in the DC, or 12 pulses available in the DC output voltage. So based on this, we classify the converters either as 3 pulse converters, or 6 pulse converters, or 12 pulse converters, or 24 pulse converters, or 48 pulse converters, and so on. So for 12 pulse operation, you can use 6, these are the various combinations of transformers. You can use 6 single phase 2-winding transformers. I mean, if single phase transformers are available to you, so how many you have to use? You have to use 6 single phase 2-winding transformers. 3 transformers will make this arrangement, and 3 transformers here. So 3 plus 3, 6 on this side, and 3 plus 3, 6 on this side. Actually, you use 3 single phase transformers and connect them as a 3-phase transformer, say star-star connected. And the other 3 transformers you use here and connect them as star-delta transformer. That's primary is star connected, secondary is delta connected. Why star-star and star-delta? I will come to that later on. So therefore, if we have only single phase transformers available to you at the converting station, and you want 12 pulse operation, for 12 pulse operation, instead of only one converter, you have to use 2 converters in series, and you have to feed them by 2 transformers. Those 2 3-phase transformers are made from 6 single phase 2-winding transformers. Now, if single phase 3-winding transformers are available to you, then you need 3 single phase 3 winding transformers. This is another combination, I mean another possibility. Or if you have 3 phase 2 pulse transformers, 3 phase 2 winding transformers available to you, then how many do you need? Only 2, as in this case. Or you use 2 3 phase 2 winding transformers. You can see only 2 transformers. This is 3 phase 2 winding transformer, this is 3 phase 2 winding transformer. This is when you use two 3 phase transformers. One is Y-Y connected, Y-Y means star-star connected, and other is Y-delta connected. Y-Y and Y-delta combination, it gives 12 pulse operation. We'll discuss about that later on. So this is these are the various possibilities of transformers, transformer connections. Now, as far as the converters are concerned, these converters, as you know, they are basically bridge converters. They comprise of thyristors or SCRs. How many SCRs will be there in one converter? If you take one converter and draw the 3-phase 6-pulse converter, for example, it looks like this. This is a 3-phase bridge converter or 3-phase 6-pulse converter. This is AC side and this is DC side. So this is 1, 3, 5, 2, 4, 6. This is how we label them. So how many thyristors do you need? 3 plus 3, 6 thyristors. But when I say 6 thyristors, I am totally wrong. Technically, I am wrong when I say that in a 3-phase 6-pulse converter, 6-pulse bridge converter, I use 6 thyristors. The most appropriate term is value. Instead of using the word thyristor, I should use the word value. I use 6 values. Value 1, value 3, value 5, value 2, value 4, value 6. Total number of values is 6. And one value basically comprises of series and parallel strings of SCRs. I hope all of you have studied series operation of SCRs, parallel operation of SCRs in your basic power electronics course. Why do we connect SCRs in series? For high voltage operation. And why do we connect SCRs in parallel? For high current operation. Imagine you have a 500 kV HVDC system. What should be the voltage rating of thyristor? 500 kV. Do you have SCR commercially available in the market with a voltage rating of 500 kV? No. What is the maximum voltage rating of a commercially available thyristor? It is only 8 kilovolts, 8 kV. So how can we connect an 8 kV and produce, give 500 kV DC transmission system? It is not possible. So therefore, for high voltage operation, as high as say 100 kV or 500 kV or more than 500 kV, you have to put many SCRs in series. And for high current operation, because current of the order of thousands of amperes has to flow through these valves in an HVDC power transmission system. If you are transmitting a power of 1000 megawatt, you may have to pass these thyristor valves may have to carry thousands of amperes of current. So to increase their current rating or current carrying capacity, you have to put many thyristors in parallel. So therefore, I will give you one simple example to understand this. Let us assume that, let me use the other pen. Let us assume that the DC voltage, the transmission voltage is 100 kV and current through the transmission link or transmission line is say 1 kiloampere. And let us assume that in the market the SCRs are available and maximum voltage rating of an SCR is 5 kV and current rating of SCR is 1 kiloampere. So we have only 5 kV voltage rating of SCR commercially available in the market, but we have to produce 100 kV HVDC link. So therefore, how many thyristors you have to put in series? 20 thyristors you have to put in series like this. This is thyristor number 1, this is thyristor number 2, this is SCR number 3 and so on, and this may be SCR number 20. So this becomes your anode, and in that case this becomes cathode. And how many, you may have to put one more string in parallel. In this case, although the current rating is 1 kiloampere, you don't need, but if current rating is more than 1 kiloampere, you may have to put another string in parallel for high current operation. In that case, this becomes your. So therefore, series operation and parallel operation of thyristor, you have to put SCRs in series, you have to put SCRs in parallel. So you have series strings and parallel strings to match the voltage and current rating of your HVDC link. In this case, each thyristor can withstand a voltage of 5 kilovolts. So you need 20 such SCRs in series. For better reliability, what we do is we increase it by 1. So instead of 20 SCRs, we use 21 SCRs for better reliability. So 21 SCRs and then parallel strings. So this becomes your value. This may be your thyristor 1. जो यहाँ पे मैंने value 1 लिखा. So value 1, although here it looks like that it's a single SCR, but my dear students, it's not single SCR. It is a series and parallel combination of SCRs. It may comprise of dozens of SCRs in series and parallel. For high voltage rating, say 500 kV line or 800 kV line, you may have hundreds of thyristors in series and parallel, and that will for your one value. So therefore, this value 1 basically is this. This is what this value 1, it comprises of series and parallel strings of SCRs. Same is the case with other values. I hope this is clear to you. For your simple low voltage converter circuits, as you have seen in the laboratory where we control a small amount of power, a few hundred volts, you need only this SCR1, value 1 means only one SCR. But for high voltage and high current operations, as in HVDC transmission system like this, a value means series and parallel combination of SCRs. So this is what value is actually. Now, if you want to increase the current rating of your converting station, suppose your converting station is designed for certain current rating, and after some time, more power it is supposed to deliver or transmit more power. So the current rating of the station has to be increased. How can you increase the current rating of a converting station? You can increase current rating of a converting station by putting thyristors in parallel, because parallel combination of thyristors increases the current rating, or putting the valves in parallel. For example, when I say thyristors in parallel, so thyristor in parallel means like this, another thyristor, similarly here, or valves in parallel. Valves in parallel means this is one valve and you put another similar valve in parallel. Or bridges in parallel. Bridges in parallel means this is your one bridge which comprises of valves like this, and you put another similar bridge in parallel with already existing bridge. So therefore, to increase the current rating of a converting station, we either put thyristors in parallel, or we put valves in parallel, or we put bridges in parallel, or a combination of these three. I hope it is clear. And if you have to increase the voltage rating of a converting station, what is the option? You put valves in series. You have already one valve, say here. You put another valve in series, or you put converter bridges in series. You have one bridge, put another bridge in series. So that will increase or a combination. Combination means both options. So that will increase the voltage rating of your converting station. Now, as far as these thyristor valves are concerned, what are the requirements? What are the desirable features of these converter valves, thyristor valves? One of the requirements is that when a particular thyristor valve is in conduction state, it is in conducting phase, it is conducting current, it should be able ideally to pass any amount of current, large amount of current, with very, very negligibly small voltage drop across it. And when the same valve is in the off state, means non-conducting phase, it should be able to block very high voltage and offer very large impedance to the flow of current. At that time, it should not allow any current to flow through it because it is in the off state, and it should be able to withstand very large voltage. Second requirement is that the peak inverse voltage of your thyristor valves should be very high. How do you determine the peak inverse voltage of your thyristor valve? It's interesting. Suppose you are suppose we have 230 volts. We take a simple single phase 230 volts AC system, and this is the thyristor, say thyristor valve. When it is conducting from anode to cathode, and okay, at that time ideally impedance is 0 and it passes certain amount of current, voltage drop or on state voltage is 0. And when this terminal is positive with respect to this, it does not allow any current to flow from cathode to anode. So at that time it blocks the voltage. Now the magnitude or the amplitude of voltage a thyristor blocks when it is reverse biased. That gives its peak inverse voltage. And for a 230 volt system, what is the peak inverse voltage? For a 230 volt system, this is 0, pi, 2 pi. This is the peak inverse voltage. This is PIV. Peak inverse voltage means the thyristor value should be capable of blocking the peak of the negative half cycle of the voltage. And what is the peak of the voltage? If RMS value of voltage is 230 volts, its peak is root 2 into 230 volts. That becomes its peak inverse voltage. Of course, minus, because it blocks negative voltage, reverse voltage. So therefore, peak inverse voltage for a 230 volt system is root 2 times 230, that is around about 325 volts. And for high voltage DC transmission systems, it is not in volts, it is in kilovolts. Your thyristor value should be capable of withstanding large peak inverse voltage. That's the second requirement. Third requirement is that there should be smooth transition of a particular thyristor value when it is going from off state to on state and vice versa. Let us take this thyristor value. Let's assume that it is in on state. After some time it turns off and it transfers current to value 3. So there should be smooth transition from outgoing value to incoming value. And after some time, if we assume that this has to transfer current to this, so this should smoothly transfer current to this value. So there should be smooth transition or transfer of current from outgoing value to incoming value, and so on. So these are the requirements of thyristor valve. Now, what type of converters are we using in HVDC power transmission systems? What type of converters are we using? The type of converter that we are using in HVDC system depends upon the energy storage element used at its output. And what are the two energy storage elements we generally use, either inductor or capacitor? A converter in which inductor is used at its output, DC output, that becomes your current source converter. And a converter which uses capacitor across the DC output, that is called voltage source converter. And it looks like this. Your current source converter is like this. I will draw just schematic. This is input and this is, see, in this is your current source converter. This is AC input and this is DC output. And what energy storage you are using? You are using inductance in series at the DC side, on the DC side. So this becomes your CSC. CSC means current source converter. And the converters, semiconductors, full converters, which you have studied in your basic power electronics course, they are all current source converters. Because if you remember, in those converters, we are not using capacitor at the output, we are using inductor at the output, right? And what about voltage source converter? A voltage source converter generally does not use thyristor. It uses modern power semiconducting device like IGBT or GTO or IGCT or power MOSFET. So it looks like this. So I will show an IGBT. It uses IGBT valves. This is three-phase input AC and this is DC. But instead of using inductance, what we do? We use a capacitance CD across its output. And this is your output voltage VD. So this is a voltage source converter, VSC. Because the voltage across its outputs is constant. The current ID can vary. In current source converter, the current is constant and you can vary the voltage. Since here current is constant, it's called current source converter, and in voltage source converter, the output voltage is generally maintained constant and it is called voltage source converter. Now, as far as current source converter is concerned, in all classical HVDC power transmission systems, the HVDC power transmission systems which are globally existing, including in India, current source converters have been used and are being used. But in modern HVDC power transmission systems, voltage source converters are used using IGBTs or GTOs. And when we use voltage source converters instead of current source converters in modern HVDC power transmission systems, we call that modern HVDC power transmission system as HVDC light, LIGHT light, or it is also called HVDC plus, PLUS. These are the names given by the companies which are the manufacturers of these. HVDC light is the brand name given by Siemens, and HVDC plus is the brand name given by ABB. ABB and Siemens, they are the pioneers in these HVDC transmission systems. So in modern HVDC power transmission systems, we do not use current source converters, we use voltage source converters, and we call the modern HVDC system as HVDC light, the name given by probably Siemens, or HVDC plus, the name given by ABB. Okay, why it is called HVDC light? This light does not mean Roshni, it means light means small, lighter in size. The modern HVDC systems are smaller in size, lighter in weight. That's why it's called HVDC light, because they use PWM techniques, and using pulse width modulation techniques, the size of magnetics drastically reduces and it becomes lighter in weight. We'll come to that later on, but mostly, since majority of HVDC systems are classical HVDC systems, I will just discuss it probably in last lecture about HVDC, modern HVDC systems, that HVDC plus or HVDC light, and most of the discussions and lectures will be discussing the classical HVDC systems using current source converters. Now, if you draw the comparison between these two converters, see, this is, I can tabulate that. This is CSC, current source converter, and in the second column, I have VSC, voltage source converter. The first point of comparison is current source converter uses reactor or inductor, and voltage source converter uses capacitor at its DC output, across its output. Second is, in current source converter, the current is constant, output current or DC current is constant. I will write here constant current. In voltage source converter, the output DC voltage is constant. So I will write here constant voltage. So CSC gives constant DC output current and VSC gives constant DC output voltage, right? Third is higher losses, and it has lower losses. The reactor, when I say inductor, it's not a few millihenry, it may be of the order of 1 or 2 henries. And when I say 2 Henry, you know, if you visit our power electronics lab, we have designed a few years back, they are 5 millihenry or 6 millihenry inductors, they are of this size. Imagine 5 millihenry, if it is of this size, what will be the size of 2 Henry? Maybe the size of this room, very large in size. And these inductors are made up of coils, and coils have got some resistance, so they produce the I square or losses. So losses are higher in current source converters because of these large inductors, whereas losses are lower in voltage source converters. Large in size and costly and costlier. I will write here smaller in size cheap. I've already told you why modern HVDC power transmission systems are lighter in weight, because they use voltage source converters, and in voltage source converters, pulse width modulation (PWM) techniques can be used, which makes the size of the converters very, very small. So converter size is large in case of current source converter, and converter size is small in case of voltage source converters. More fault tolerant, and more reliable. Here I will write less fault tolerant and less reliable. This is another comparative point of comparison between the two. Current source converters are more fault tolerant. It is the inductance which is in series with the current source converters at its output. At their output, it's a huge inductance, and in the event of a fault or a short circuit, this inductance limits the rate of rise of fault current, and it limits the magnitude of fault current, makes it more fault tolerant and more reliable. Whereas in voltage source converters, we don't have any current limiting reactor. We have only a capacitor across, so it cannot limit the magnitude of fault current. So voltage source converters are less fault tolerant and less reliable. Next is simpler, and this is complex. Simpler operation, this is complex operation. Current source converters are very easy to operate, very easy to control. Instead of operation, I should write control. Simpler control and complex control. Voltage source converters have complex control. I'll come to that. We'll come to that later on. Okay, simpler control, complex control. Faster control, sluggish control. Because I will write within brackets, because of presence of capacitor. Capacitor is connected across the output of a voltage source converter. That makes it sluggish in control. Whereas we don't have any capacitor in case of current source converter, so control is quite fast. And finally, difficult, I should write series expansion of converters is difficult. Here I will write parallel expansion of converters is easy. I mean, if you want to expand a particular converting station, if you are using current source converters, you may have to connect the various bridges in series, and that becomes a bit complex, whereas it is easier to connect converters in parallel in case of voltage source converters. So these are various points of comparison between current source converter and voltage source converter. So in all classical HVDC power transmission systems, we are using current source converters, whereas in modern HVDC power transmission systems of low ratings, we are using voltage source converters. Now, see, this is our classical HVDC power transmission system using current source converter. The DC line current is ID and DC line voltage is VD. In current source converters, ID, that's DC line current, transmission line current, is always maintained constant with the help of controller, and voltage is variable. And the parameter with the help of which, in case of a converter, you can vary the voltage. What is that parameter? Firing angle or delay angle. You have studied in your basic power electronics course. When you change the delay angle or the firing angle of a converter, whether it is a three-phase converter or single-phase converter, the output, average output voltage changes. And it is easier to control voltage rather than current. That is why in current source converters, we always maintain DC line current constant, whereas we can very easily vary voltage for control of the power. And it is very easy to vary the voltage, to control the voltage using firing angle control or delay angle control. Okay. So that was about the first part, converters. Lastly, I will add one more thing. I will give you the present scenario of various power semiconducting devices which are available in the market. Their voltage and current ratings. I will not note down that here. I will just read it from here, and I will take a photo snap of it and share with you on WhatsApp group. The various power semiconducting devices which are available are thyristor. Thyristor means SCR, GTO, gate turn-off, thyristor IGBT, SIT, MCT, and power MOSFET. Maximum voltage rating of an SCR, which is presently available, commercially available in the market, is 8 kilovolts. That's 8,000 volts. Note it down. GTO, which is available in market, has maximum voltage rating of 6,000 volts. That is 6 kV. IGBT is available in a low voltage rating in the market, that is 1700 volts. SIT is available up to 2500 volts. MCT is available up to 3000 volts. And power MOSFETs are available in very low voltage rating, that is 1000 volts, maximum voltage. That is about voltage rating of various power semiconducting devices commercially available in the market. What about maximum current rating? Maximum current rating of thyristor or SCR, 4000 amperes, that's 4 kiloamperes. GTO has higher current rating, 6000 amperes, that is 6 kiloamperes. IGBT, 800 amperes. SIT, 800 amperes. MCT, 400 amperes. And power MOSFET, only 100 amperes. Now, gating, conduction drop or on-state voltage. Conduction drop means when a particular power semiconductor device is conducting, it is in the on state, there is some voltage drop across it. And that's called conduction drop or on-state voltage. It is only 1.2 volts in case of thyristor, 1.2 volt only. For GTO, it is almost double, 2.5 volts. For IGBT, it is 3 volts. For SIT, it is 4 volts. For MCT, it is 1.2 volt. And for power MOSFET, it is less. Switching frequency is very important, especially if you want this PWM operation. The main drawback of SCRs or thyristors is that you cannot switch them at higher frequency. Their switching frequency is very, very low, only 1 kilohertz. The switching frequency of GTO is higher, slightly higher, 5 kilohertz. IGBT, they are available up to a switching frequency of 20 kilohertz. SIT 20 kilohertz, MCT 20 kilohertz, and most importantly, power MOSFET up to 100 kilohertz. You can switch a power MOSFET up to 100 kilohertz. Development target. Development target means what is the target of the industry, maximum voltage and maximum current. Maximum voltage rating they are targeting in future for SCR 10 kilovolts. Presently it is 8 kilovolts. They are now targeting to develop SCRs for up to the voltage of 10 kilovolts. GTO also 10 kilovolts. IGBT 3.5 kilovolts. SIT 5 kilovolts. MCT 5 kilovolts. And power MOSFET up to 2 kilovolts. And maximum current rating development target is like this. Thyristor 8 kiloamperes. Right now thyristors are available in market up to a maximum current rating of 4 kiloamperes. Now their target is to increase it from 4 kiloamperes to 8 kiloamperes. That means to double it. GTO 8 kiloamperes, IGBT 2 kiloamperes, SIT 2 kiloamperes, MCT 2 kiloamperes, and power MOSFET 0.2 kiloamperes. 0.2 means about 200 amperes. It's not possible to have very high current rating of power MOSFETs. So this was the first part and the most important part of your HVDC power transmission system, that is converter. What is the second important part? Second important part you can see from your schematic diagram is converter transformer. Converter transformer. This converter transformer is used, you can see in the diagram, we have shown it with the help of these circles. Let me draw it again for your reference. Bipolar link, I will show bipolar HVDC link. This is plus, minus. This is the smoothing reactor LD. This is ID, this is ID. This is your converter transformer, 3-phase. A is to 1, YY, that is star star connected. Another converter transformer feeds this converter, second converter. It also has transformation ratio of A is to 1, but it is Y delta or star delta connected. Similarly, on the other side, you have 1 is to A transformation ratio, and it is YY connected. Again, 1 is to A, and this is Y delta connected, just like the other side. And this is the bus, and this is 3-phase AC. This is the ground, this is ground, and you may have harmonic filter here. This is harmonic filter here, and this is harmonic filter here. So these are the converter transformers. So you have YY connected converter transformer here and Y delta connected converter transformer, which gets supply from the same bus. Why do we use YY and Y delta? It gives a phase shift between the voltages of 30 degrees, and that gives us 12 pulse operation. If you use only one converter and use only one converter transformer, it gives 6 pulse converter operation. But if you use 2 converters in series and feed them with 2 transformers, 3-phase transformers, one is YY connected and another is Y delta connected, the phase shift between the output voltages, secondary voltages of these 2 transformers is 30 degrees. And you will see in future, we will study inshallah 12 pulse operation of converters. The output voltage, this VD plus minus VD, and the output, it will be 12 pulse voltage. So these transformers, which are connected as star star and star delta, they result in 12 pulse output voltage on both sides. Now this converter transformer is a special transformer, unlike the conventional transformer that we use, conventional power transformers that we use in power systems, because it has to carry huge harmonic currents. It has to handle harmonic currents. Whenever a thyristor converter operates, it distorts the current waveform. So harmonics are injected in the current, so that those harmonic currents have to flow through the winding of transformer. Transients also it has to take care of, and it should have the arrangement for tap changing, online tap changing. We call that OLTC. OLTC. OLTC means online tap changing. These are not simple transformers, these are tap changing transformers, online tap changing transformers. Now, as far as these transformers are concerned, they are high voltage transformers, and you cannot put winding very close to the yoke of the transformer. The winding has to be properly insulated because of very high voltage stress across the windings. That's first point. Second point is that since the currents which are flowing, including the magnetizing current which is flowing through the converter transformer windings, they are very rich in harmonics. They don't carry sinusoidal currents because of the thyristor converter operation. They carry non-sinusoidal currents. So because of harmonics present in the currents, the mutual flux in the core of the transformers is very rich in harmonics. And these harmonics increase the eddy current losses in the transformer windings, transformer core and tank, and they produce sometimes they may produce hot spots in the transformer core. Second point. Okay. And the third point, which makes it different from the conventional power transformers which are used at power stations and grid substations, is that if there is a fault, say for example there is a fault on the DC side, a huge current will flow, and the magnitude of current has to be limited this current will flow through the transformer windings also. So in order to limit the magnitude of fault currents, that these converter transformers are designed with high leakage impedance, because in case of large fault currents, it is the leakage impedance of transformer which will limit the magnitude of short circuit currents, which will limit the magnitude of fault currents. Therefore, these converter transformers are designed for large leakage impedance as compared to conventional power transformers. And another thing is that these transformers are fitted with online tap changing arrangement. Online tap changing is done for voltage control and for reactive power control. We'll come to that at a later part. We'll see how online tap changing is used for reactive power control and voltage control. So that makes the converter transformers different and special as compared to power transformers used in conventional power systems. Okay, so I will stop here, because if the length of video lecture is more, then it becomes very difficult for me to upload it. It takes the whole night to upload. So we have discussed we are discussing the principal parts, the main components of an HVDC power transmission system. They have identified that what are the main components: thyristor converters, converter transformers, harmonic filters, grounding rods, and these smoothing reactors and reactive power compensators. Out of these 5 or 6 parts, today we have discussed 2. One is converters and another is converter transformer. Inshallah, in next lecture we will discuss other parts of the HVDC bipolar power transmission, HVDC link or HVDC power transmission system. So please go through this lecture, listen to it, make notes, prepare notes, go through them. You may have some books, some supporting material also. Read it, discuss it among each other, discuss it with me on the WhatsApp group, or you can put your comments on the YouTube channel. If there are any queries, I am ready to interact with you, clear your doubts. So I am there for you. Let's have interactive sessions, discuss with each other. So please take these lectures seriously, learn about this technology, study this subject, and come up with discussions. Any doubts, we'll discuss on the group. Thank you very much.